Welcome back to the deep dive. We recently looked at how electric current creates heat, that Joule heating effect. Very useful for ovens, toasters, that sort of thing. Very tangible.
Very tangible, yes. But there's this other side to electricity, isn't there? Something silent, invisible.
Exactly. What if that same simple wire carrying that same current could do something, well, almost magical?
Yeah.
Something that actually built the foundation for, I don't know, radios, TVs.
That's precisely the journey for today. We're diving into the source material that finally connected electricity and magnetism, two worlds that seem totally separate.
Right.
Our mission, really, is to trace that connection from, believe it or not, an accident all the way to the safety systems working invisibly in our homes right now.
And the core idea, it sounds so simple when you say it now.
It does, doesn't it?
An electric wire carrying current just acts like a magnet.
Exactly like a magnet. But yeah, for ages, nobody saw the link. They were just studied completely separately.
So who made the connection? When did that change?
That big moment belongs to Hans Christian Ørsted back in 1820. He was, a big name already. But the discovery itself, pure chance, apparently.
Really? How?
Picture this. He's doing some experiment. There's a wire carrying current. And just sitting nearby is a little magnetic compass.
Okay.
The moment the current goes on, the needle, it just twitches, deflects.
Ah, that little twitch. That's the key.
That was everything. That tiny movement was proof positive that the moving charge, the electricity, was creating its own magnetic field. A field strong enough to push a compass needle.
So they weren't separate forces at all.
Not at all. Two sides of the same coin, really. Electromagnetism. And yeah, that discovery, it paved the way for radio, fiber optics, so much modern tech.
Yeah.
And they even named the unit of magnetic field strength the Ørsted after him. Shows you how big a deal it was.
Okay, let's unpack this then.
Yeah.
If a current-carrying wire is a magnet, it must have a magnetic field, right?
Yeah.
But how do we picture that? It's invisible.
We use the idea of magnetic field lines. Think of the field as the zone of influence around the magnet, or our wire where its force can be felt.
And the lines map that influence.
Exactly. To get a feel for it, let's start with a simple bar magnet. North pole, south pole, like poles repel, opposites attract. Basic stuff.
Right, the classic school experiment with the iron filings.
Precisely. You sprinkle those filings on paper over a magnet, give it a little tap.
And they snap into a pattern.
They do, because each tiny filing feels the force and lines up. That pattern shows us the magnetic field lines. And these lines, they follow some very specific rules.
Okay, what are the rules for this invisible map?
Rule 1. The lines show both magnitude, strength, and direction. By convention, we say they emerge from the North Pole.
Okay.
Circle around and then merge back into the South Pole outside the magnet. But here's the important bit. They continue inside the magnet, from south back to north.
Ah, so they're complete loops. Closed curves.
Always closed curves. That's rule 2, basically. They never just start or stop. Rule 3. How close together the lines are tells you how strong the field is.
So crowded lines mean stronger force, like near the poles.
Exactly. Where they bunch up, the magnet's pull is strongest. And rule 4, this is critical. No two field lines ever cross each other.
Why not? What would happen if they did?
Think about it. If they crossed at a point, what would a compass needle do right there?
It would have to point in two directions at once.
Which is impossible. A compass needle can only point one way. So
Right.
physics dictates they cannot cross. It maintains the order of the field.
Okay, that makes sense. So that's the field around a normal magnet. Now back to Ørsted's wire, a straight wire carrying current. What does its field look like? It can't be the same bar magnet pattern, surely.
No, you're right. It's different. And actually quite elegant. Experiments show the field lines form perfect concentric circles around the wire.
Concentric circles,
Yeah.
like ripples on a pond.
Exactly like ripples. Centered right on the wire itself. Invisible magnetic ripples spreading outwards.
And I assume the strength changes, like with the bar magnet.
It does. Two key things here. 1, increase the current flowing through the wire.
The field gets stronger.
The field gets strong. Yes, the magnetic ripples become more intense. 2, move further away from the wire.
Field gets weaker.
It gets weaker quite quickly, actually. Those concentric circles get bigger and more spread out as you move away. The influence drops off.
Okay, so we have these circles,
What?
but circles, well, they spin, right?
Yeah.
How do we know which way the field is circling? Clockwise, counterclockwise.
Good question. We need a direction finder. And luckily, there's a really handy tool for this. It's called the right-hand thumb rule.
The right-hand thumb rule. Okay, sounds useful. How does it work?
It's quite intuitive, actually. Imagine you grab the wire with your right hand.
Okay.
Got it, right hand. Now, point your thumb in the same direction that the electric current is flowing along the wire.
Okay, thumb follows current.
Then, the way your fingers naturally curl or wrap around that wire, that shows you the direction of the magnetic field lines.
Ooh.
That's clever.
So thumb for current, fingers for field direction.
Simple as that. It gives you the spin instantly.
Let's try it. Say a big power line running east to west over a field, current flowing west.
Okay, current west. So, point your right thumb west, wrap your fingers around the imaginary line.
My fingers curl.
Yeah.
Downwards underneath the wire and upwards on top.
Exactly. So below the wire, the field points, say, south. Above the wire, it points north. If you looked at the wire end on from the east, the field would be circulating clockwise around it.
Wow. So every power line has this invisible magnetic whirlpool spinning around it?
Constantly, as long as current flows.
Okay. Now, what if we mess with the shape? What if we take that straight wire and bend it into a circle, a circular loop?
Ah, good question. When you make a loop, think about each little segment of that wire still creating its own circular field lines according to the right-hand rule.
Right.
But now, inside the loop, all these little circular fields start to add up and reinforce each other. They sort of merge as they expand towards the center.
They get bigger.
The circles get so big that right at the very center of the loop, the field lines actually look like straight parallel lines running perpendicular to the loop itself.
Interesting. So it focuses the field in the middle.
It does. And if you want even more focus, even more strength.
You stack the loops, make a coil.
Precisely. You wind the wire into a tight coil, like a spring or a cylinder. That's what we call a solenoid.
Okay, a solenoid.
Each turn adds its magnetic field to the other. So if you have, say, unturns in your coil, the magnetic field inside becomes n times stronger than just a single loop.
That sounds powerful.
It can be. And what's really useful is that inside a long solenoid, the magnetic field is almost perfectly uniform. The field lines are straight, parallel, and evenly spaced.
Like inside a bar magnet.
Exactly. The whole solenoid behaves just like a strong bar magnet with a clear north pole at one end and a south pole at the other.
Which means if you put something like a piece of soft iron inside that coil,
You've just made an electromagnet. The iron core becomes strongly magnetized when the current is on and loses most of its magnetism when the current is off.
so you can switch a powerful magnet on and off.
And that control, that ability to switch magnetism is fundamental to countless technologies. Think cranes lifting scrap metal, relays, doorbells.
Okay, I see. So current makes a field. Now let's flip it. Does the field affect the current? I remember you mentioned André-Marie Ampère.
Yes, Ampere had this brilliant insight, following Newton's laws, really. If the current-carrying wire pushes on a magnet, like Ørsted's compass.
Then the magnet must push back on the wire, right?
Yeah.
Equal and opposite force.
Exactly. The magnet exerts a force on the conductor carrying the current. There's a classic demonstration for this.
Tell me about it.
You take a light rod, maybe aluminium, and suspend it horizontally so it can swing freely. Then you place it between the poles of a strong horseshoe magnet.
So the rod is sitting in the magnetic field.
Right. Now you pass an electric current through the rod. Instantly, the rod gets pushed. It moves. It experiences a force.
Yeah.
And get this, if you reverse the direction of the current flowing through the rod,
The rod moves the other way.
it moves the opposite way. And if you leave the current the same but flip the magnet poles, reversing the field direction,
It moves the other way again.
moves the opposite way again. It clearly shows the force direction depends on both the current direction and the field direction.
Okay. And is there a way to get the most force, the biggest push?
Yes. The experiments show the force is strongest, the displacement is largest when the wire and the current in it is positioned at right angles, 90 degrees perpendicular to the direction of the magnetic field lines.
Perpendicular is key for maximum force.
Absolutely. Field, current, and the resulting force like be mutually perpendicular for the biggest effect.
So now we have three things at right angles: field, current, and the resulting motion or force. How do we keep track of which way the wire will move? We need another rule, don't we?
We do. And this one involves the other hand. It's Fleming's left-hand rule.
Okay, left hand this time. How does it work?
You take your left hand, stretch out your thumb, your forefinger, and your middle finger so they are all perpendicular to each other, like making a little 3D axis.
Right, got it. Thumb, forefinger, middle finger, all at 90 degrees.
Now, assign each finger. Your forefinger points in the direction of the magnetic field, F for forefinger, F for field.
Okay, four-finger field.
Your middle finger points in the direction of the current. Maybe think C for center finger, C for current.
Middle finger, current.
Then your thumb automatically points in the direction of the resulting motion or thrust or force. Think M for motion or T8 for thumb thrust.
Field, current, motion.
Yeah.
FBI, almost. Wait, no, four-finger field, middle current, thumb motion. Okay.
That's the one. It reliably tells you the direction of the force.
And this principle, this force on a wire in a field, this must be huge technologically.
Oh, absolutely fundamental. This is the principle behind every single electric motor. Your fan, your washing machine, electric cars, they all work because of this force.
And generators, too.
Generators use the reverse effect, which we might explore another time, moving a wire through a field to create current. But loudspeakers, microphones, they also rely on this interaction between currents and fields. It's everywhere.
It really is the engine of the modern world. Now, you mentioned something surprising, connecting this to our bodies. Medicine.
Yes, this is fascinating. We tend to think of electricity in wires, but our own bodies run on tiny electrical currents. Nerve impulses, you know. When you touch something, signals travel along nerves. Your heart beats due to electrical pulses. Your brain activity involves currents.
Okay, tiny currents.
Incredibly tiny. But remember Ørsted, any current creates a magnetic field. Even these minuscule ionic currents in our nerves generate equally minuscule magnetic fields around them.
You're kidding. We have magnetic fields inside us.
We do. They're incredibly weak, maybe a billionth of the Earth's magnetic field, but they're there.
Can we detect them?
Amazingly, yes. There's a technology based entirely on detecting and mapping these ultra-weak biological magnetic fields. It's called magnetic resonance imaging, or MRI.
MRI, of course. I never connected it to nerve currents.
Well, it's a bit more complex, involving nuclear spins and radio waves, but the fundamental link is there. By using powerful external magnets to align things and then detecting the subtle magnetic signals from tissues, doctors can get incredibly detailed images, especially of soft tissues, without any harmful radiation.
So Ørsted's twitching compass needle ultimately led to technology that lets doctors see inside our brains.
In a way, yes. It's all part of understanding and harnessing this fundamental force.
That's incredible. Okay, let's bring this right back home. Literally, we've seen the big tech, the medical marvels. But how does all this electromagnetism keep us safe in our own houses? In the wiring?
Ah, yes. Domestic circuits. Typically, we get AC power, alternating current, at around 220 volts here. And coming into your house, you essentially have 3 key wires.
3 wires, what are they?
You've got the live wire, often with red insulation. This carries the high potential, the push for the current. Then the neutral wire, usually black, which completes the circuit, providing the return path.
Live and neutral. Got it. What's the third?
The third one is arguably the most important for safety. The earth wire, usually green.
The earth wire.
Yeah.
Why is that one so critical, especially for things with metal bodies, like a fridge or a toaster?
Okay, imagine the wiring inside your toaster gets frayed, and the live wire accidentally touches the metal casing.
Oh, that sounds bad. The whole metal body becomes live.
Exactly. It's now at 220 volts. If you then touch the toaster, and you're standing on the ground, you become the easiest path for the current to flow to the earth.
I'm going to get a nasty shock.
Potentially a fatal one. Now, the earth wire prevents this. It's physically connected from the appliance's metal casing directly to a big metal plate or rod buried deep in the ground outside your house.
Okay, so it's grounded.
It is. And crucially, that earth wire provides a path of very, very low electrical resistance, much lower than your body's resistance.
So if the casing becomes live?
The electricity takes the path of least resistance. Instead of going through you, the huge fault current surges down the earth wire straight into the ground. It keeps the appliance casing potential safely at 0 volts relative to the earth.
It basically diverts the danger away.
Instantly and effectively. It's a lifesaver.
Okay, so that handles leakage. What about other electrical dangers, like things suddenly drawing way too much current?
Right, you're talking about short circuits and overloading. Big risks, too.
What's the difference again?
A short circuit is when the live wire and the neutral wire accidentally touch directly. Maybe the insulation between them gets damaged. Resistance drops to almost 0.
And the current skyrockets.
Massively and instantly. Very dangerous, causes sparks, fires. Overloading is a bit different. That happens when you plug too many high-power things into one socket or circuit.
Like running a kettle, a microwave, and a heater all at once from the same outlet.
Exactly. Or sometimes there might be an unexpected voltage surge from the supply itself. Either way, the circuit ends up trying to carry more current than its wires are safely rated for.
And that leads to overheating.
Overheating, melting insulation, potential fires again. Both short circuits and overloading mean dangerously high current.
So how do we protect against that? We need something to just cut the power if the current gets too high.
And that brings us full circle, back to the very first thing we discussed today.
Joule heating, the heating effect.
Precisely. The solution is the humble but essential electrical fuse. Or nowadays, offer a circuit breaker, which does the same job but is resettable.
How does the fuse work using heat?
A fuse is incredibly simple. It's just a special, thin wire inside a protective casing. That wire is designed to melt to fuse at a very specific temperature, which corresponds to a specific maximum safe current.
So it's a deliberate weak link.
The perfect weak link. If the current flowing through it suddenly surges way too high because of a short circuit or overload, that thin fuse wire heats up incredibly fast,
Does red hot.
melts almost instantly, breaks the connection, and physically stops the flow of electricity dead in its tracks.
Protecting the rest of the circuit and the expensive appliances plugged into it.
And preventing a potential fire. All thanks to the predictable heating effect of current.
Wow. We have covered a lot of ground. Started with Ørsted, seeing a compass twitch.
Which revealed electricity and magnetism were linked.
Learned about mapping invisible fields with lines that never cross.
Figuring out the field direction with the right-hand rule.
And then the force direction with Fleming's left-hand rule.
Which led us to motors and, surprisingly, even medical imaging like MRI.
And finally, seeing how earth wires and fuses use these very principles to keep us safe every day at home.
It really shows how interconnected these concepts are. Electricity and magnetism, they're not just related, they're fundamentally intertwined. Cause and effect, back and forth.
It makes you think.
It does, and it leads to a rather interesting final thought, doesn't it?
Go on.
Well, we've established that tiny currents in our nerves create tiny magnetic fields. And we know from Fleming's rule that a current-carrying conductor experiences a force when it's in a magnetic field.
Okay, where are you going with this?
We live on a planet with a pretty significant natural magnetic field, the Earth's own field.
Right.
So if our nerves carry currents, however weak, and they exist within the Earth's magnetic field, could that planetary field be exerting some kind of subtle, constant influence on our biological processes?
Yeah.
On our sense of direction, maybe, even if we don't consciously feel that force?
Huh. Does the Earth's magnet pull on our nerves?
Oh, yeah.
That's quite a thought.
Something to mull over, perhaps, next time you feel a bit of static electricity, or just wonder which way is north.